We'll go ahead and get started. First, then, I just want to talk about the series itself. Just take a couple minutes to do that. For a while, we've wanted to present to the community, the IU community, and local places like Crane, the opportunity to talk about scientific visualization. We have a lot of kind of expertise in our group at the Advanced Visualization Lab, and we share it with people whenever we can, often one-on-one or small groups. But we wanted to have a kind of a bigger session where we can share it to a wider community and get some more interactive, and then also let people know what's out there and what we can do and what the high performance computing group at IU, the research technologies group, offers people. So today, of course, is the introduction to scientific visualization. So it'll be pretty much a whirlwind. I may have to talk pretty fast or skip some slides. Next week, I'll be presenting on something a little more specific and hands-on, perhaps, and that's the PairView visualization tool. And so that's a tool that's kind of generic, works mostly with spatial data of some sort of another, and we use it both interactively, and we also use it sometimes to produce little animated movies once we've decided on some parameters. Then in the third week, Jeff, who's up at in our Indianapolis campus, we'll talk about 3D digitization, both from the capturing side, so with scanners, with photogrammetry, and then also on the output side, physical output, as well as other types of output. So we'll talk a little bit about 3D printing and other things. Then I'll be back to talk about doing visualization using virtual reality. So in the back of the room, it's not set up right now, but there's a virtual reality equipment in one of those cabinets. We'll have that set up, and then I'll talk about it. Mostly I'll show pictures and videos, and then afterwards we can do some demonstrations of that. So we'll talk about ways we use virtual reality for scientific visualization. The following week, Chauncey, another one of our colleagues from Indianapolis, will talk about augmented reality with visualization. And then we have an expert on geographic information systems in our sister group, Justin Peters. So he will be talking on using RED, which is the research desktop available from Research Technologies here at IU. And then Andreas, who's part of the information visualization group here on the 4th floor of Luddy, will talk about Internet of Things visualizations along with augmented reality that he's using. Then myself or someone else will talk about volume rendering, different ways of choosing colors and things like that to do good kind of look inside objects. Dave Reagan, who's sitting in the back, will talk about some InfoViz and InfoViz tools. Chris, who has departed for another engagement, will talk about advanced media, including big screens like this and big capture things, things like technologies like that. And then I'm going to talk about VTK, which is a toolkit for creating visualizations with an API, with a program. And specifically, we'll look at VTK.js, which is a web version of VTK. So you can actually create visualizations that can be easily deployed onto a web browser. Then Kati Borner and her colleague Bruce Hare will also from the visualization, information visualization group here in Luddy, will talk about their work doing data visualization and expressing literacy. Then it's Thanksgiving. And then I'm going to talk about VMD, which is the visualization of molecular dynamics. And we'll do that. So the PairView one here also will be on the research desktop. VMD will be on research desktop. And then possibly Dave Reagan will be joining us again to talk about brain diffusion imaging if all goes well, I guess, right? So that's our schedule for this semester. We're hoping that if it's successful, which so far it looks pretty good, we'll continue this on into the future. Hello.
Thank you.
Welcome. And so this will be kind of our first go round. All right. So I'm already needing some water. I need the focus. There we go. All right. So today I'm going to talk about. So I'm Bill Sherman. I'm in the Advanced Visualization Lab. Did I say that? We're talking about some data, some perception, some design issues with scientific visualization. And so to start us off, I'm going to talk a brief history of visualization. So this isn't necessarily the very first visualization, but just some early visualization from 1,000 years ago from Al Bruini, who was looking at phases of the moon and kind of the relationship of the Earth to the phases of the moon, and plotted that out, again, about 1,000 years ago. Here's an early map from about 800 or so years ago, where this was trying to encompass the world. It's circular with the recognition that the world is spherical, and it has the center of the Earth at this point is Jerusalem, and in this map, east is up. So everything is kind of focused around Jerusalem in this map from the Middle Ages. Then I want to talk about a couple of examples where visualization was used to solve some problems, some early examples. So all these little black bars here, these basically represent coffins. So this is an area of London, and this is where people were dying pretty rapidly in this one region of London. And so in order to figure out what was going on, John Snow here was looking at these are, yeah, specifically cholera deaths, right? He took a look, all these red circles are where there are water pumps. There's one off the map here a little bit, but all these water pumps in this area, and you can see that a lot of the deaths are happening about this water pump right in the center. So just doing this one simple little thing, plotting where things happen, it's kind of a rudimentary heat map. If you're familiar with that, we'll maybe look at that in a later lecture. But you can see that things are kind of clustered. Lots of things on this street, even some of these outliers, when he interviewed people, these would be people who happened to pass by Broad Street here on their way to or from work and get water from that pump. Now there is one kind of anomaly here in that there's not a lot of deaths around. This is a brewery here. There were not a lot of deaths around this brewery, and this is because the people who worked in the brewery got free beer, so they actually did not go out and drink from this pump. And so they kind of saved themselves that way. So that was one early kind of utilitarian visualization. This is kind of a classic one. There's a statistician, Edward Tufte, who talks a lot about visualizations, and this is one of his favorites, in that there's 6 different variables showing this march, Napoleon's march into Russia, toward Moscow, and then his retreat. So the thickness of this plot is number of Frenchmen, right, which is dwindling, and then they are defeated and they retreat. And a lot of this is from the winter. So these lines here, these vertical lines, are giving us temperature readings, and it's not exactly Celsius, but it is 0 is freezing. So these are below freezing temperatures here, and so you can see what's happening as they march. There's also spatial information. This is more or less the path that was taken. There was one branch here that went off and then retreated early. And then there's also time, because they marched this way and then they marched backwards. So there's also time involved in this. So several different variables all expressed in this one kind of fancy chart that really, tells a story of what happened there, right? And then one other historic one I want to talk about is this one done by Florence Nightingale, along with her colleague, whose name is over here. William Farr. So Florence Nightingale felt like the reason people were dying in a lot of these battle hospitals was because of bad food or things of that nature. But then she plotted kind of what was happening. These black areas are mortality, and this is time of year. And she plotted some other characteristics and realized that really the deaths weren't necessarily from bad food. It was more from bad hygiene, and bad hygiene in the hospital itself. And so she and William Farr took this to actually Queen Victoria and had some laws passed on how hospitals had to keep themselves relatively clean. So again, using this data to enact something positive and learn something. All right, so that was our brief history of visualization. So now, as this workshop series is focused on scientific computing or scientific visualization, Kati Borner teaches and others on campus teach classes more focused on information visualization. I want to kind of keep it in that direction mostly, but there'll be we'll touch on information visualization a little bit. So this is a little map of the visualization process that a colleague of mine did several years ago, where we kind of go from the natural phenomenon to the representation, the representation in graphical form through these 5 steps. And so we start with the phenomena, right? So there's something in nature that we want to study. and to understand. So in this case, specifically tornadoes, tornadic behavior, because we want to be able to warn people with sufficient foreknowledge, amount of time to do something about it. So we want to study that. Then we go to the language of science, which is math, and all these differential equations and partial differential equations that talk about, air pressure and air temperature and things like that. I actually have no idea what most of this means. I didn't go that far into math, right? So the next step is where I come in, right? So this is the math step. So nature follows a lot of these parameters, and social sciences also find that there's a lot of calculus that comes involved in how demographics move and things like that. So this is where, on the computational side, we come in. We take those formulas. This is in Fortran, which is not something I'm going to use, but we take those formulas and we convert them into discrete steps and discrete entities, discrete time steps and discrete spatial steps in order to process all that as best we can, right? And as our computers get faster, we make those steps smaller and smaller. So we don't actually solve the problems any faster. We just solve them better because we make them more refined. So we run this on our supercomputers or on our desktop these days. We can do a lot of that, and we get this kind of stuff, right? A lot of information in space and or time, right? However we want to do it. And then sort of my job and the job of the visualization community and other people who want to do visualization is take those numbers and put them back into something we can look at. Not necessarily to make it look realistic. So in this case, it kind of does. It is made to be a little bit realistic. That's always actually a nice first step in that it kind of gives us some confirmation that we made, we didn't lose ourselves in one of those other in-between steps. And then if it kind of looks correct, now we can like slice in here and add some colors that are unnatural, but tell us some information about that, right? Okay, so we've gone through the whole process. We have the numbers, the visualization. I want to look back at the numbers. Is anyone else familiar with Anscombe's quartet? So if you look at these numbers, for the most part, they look pretty random with maybe one exception, right? Does anyone see the exception? This column here is almost all 8s. But everything else looks kind of random. The thing is, each of these pairs, each of these XY pairs has these statistical qualities, right? There's 11 of them. They all have the same mean in X and Y, same as each pair. The variance for X and Y is the same for each, and the correlation between X and Y is the same, so they both plot to the same linear plot. The thing is, if we're just looking at the numbers and these basic statistics, that doesn't tell us the whole story, right? Here's those same data sets, 1, 2, 3, and 4, and here's all the 8s, right? And they all have the same linear plot, but they're clearly not all the same data. This one's not even linear at all, right? It's a parabola. This one's more noisy, but it gives us the same line. This one obviously has a different line than what we plotted. It just had this one outlier which changed the graph. And this one has a much different plot, and this one's serious outlier which causes the whole plot to change, right? So this is why we visualize, right? Is because of this. You can figure that out if you looked at all the numbers, but you can figure it out a lot more quickly this way. All right, so that's what we want. We want some visualization. So this is some concepts that we're borrowing from Peter Gallison at Harvard, in that visualization is kind of this means to communicate between communities, right? So in this, he uses this analogy to like trading, like Marco Polo going from culture to culture and taking information back and forth. So we can kind of go from one place to another. So if I'm an astrophysicist or an atmospheric researcher in our storm thing, we can explain parts of how the weather phenomenon works by adding pictures to it, adding annotations to what's happening. And so, part of our team, the visualization team, is to help make that happen or help teach other people how to make that happen for their own data, right? And so we're kind of this agent who is, we're help do the translation between communities, right? And so here he's got these three kind of classes of where the trading is between, right? So one is just the scientist's data and the scientist. And then once the scientist has figured things out, their research and a researcher in a different community, different science community. And then that community expressing it to the public in general. So there's all these different places, right? We're going to do a lot different kind of visualization here than we're going to do here. This one will be a little more fancy, a lot more probably simplified if we're going between the scientist and the public. But a lot of the same concepts are going to apply, because if we use the wrong colors, we might find that we're lying to ourselves when we're doing our research. So it's important to know this at the visualization concepts at every stage. So we'll talk about this a little bit later, but there's kind of this, we want you to get from data to understanding that data. And so there's two ways to do it. We can send it through our statistical analysis and get those numbers, right, of what things look like, but that's not really the only path we want to take. We want to take a look at the pictures, and then we're going to do some iterating, right? We might find something out and then think about it and say, oh, what if I run, this kind of analysis on it? And so once I have some sort of inkling of what might happen, I might go back down here, do some do some processing on that, and then take a look at the results again, and then eventually, hopefully, learning something about it. All right. So in the end, this knowledge requires that we're talking to people, right? We have to, including ourselves, the scientists. So I want to talk a little bit about the notion of design for humans, right? So I'm not going to talk about the sensory system to save some time, but we'll go a step up and talk a little bit about human comprehension and some of the stuff that happens maybe that even psychologists don't know exactly what's going on. So our comprehension, though, along with our senses, does kind of put this filter on what data we see. So a lot of times you'll see people use colors that follow the rainbow, right, from ultraviolet or from violet to red. But there's perceptual things in there where the change in, say, brightness isn't consistent across from purple to red, and so you add these artifacts that might not be there in the numerically or in the wavelength that's being emitted, but your brain sees them a little bit differently because of the way your cones work in your eyes, and so there's some filtering there at the sensorial level as well. But we want to talk a little bit more about the cognitive processes that kind of happen. And so I'm going to talk briefly about generalization, semiotics, which is the study of signs. We'll talk about representing ideas briefly, and then I'll spend a little bit of time on this notion of Gestalt design and or perception, which I'll get into in a moment. So I like to start by talking about generalization. It's one of the things that as people we're good at, right? Sometimes it works to our disadvantage. We overgeneralize things, but to start with, maybe it works pretty well. If you see something, that has 4 legs on it, or in this case, 2 legs over there, and at a flat surface, that's a table or perhaps something to sit on, and it doesn't have to look exactly the same. If you see something like this may not work too much anymore because people don't recognize that receiver too much anymore. But anyway, you can recognize, at least in the past, recognize this as a phone because it has something to listen to, something to talk into, and this pattern of buttons. Right now, these days, the pattern of buttons is probably what gives it away. But we can see kind of what that object is, right? And then beyond generalizing, we can use analogy to express ideas that if you're already familiar with, how I don't know if I have a good idea on the top of my head, but how a chair works, you can talk about how the support of weight for other objects or something like that. Not a great analogy for my analogy, but basically it lets us, take another step or help someone else take another step in understanding based on something they already understand. All right, and a couple slides on semiotics, which is, as I said earlier, the study of signs and symbols. So a sign is basically just a convention, right, that we've applied meaning to. in the place of words, or actually words themselves are well, they're symbols. And so you can have this complex notion represented fairly quickly. People can recognize it like street signs and understand what's going on without having to do a lot of thinking, right? And then a symbol is along those same lines, but it's a little bit more arbitrary, right? So a sign is something that maybe is easier to figure out. A symbol is something that really doesn't have any meaning other than what we give to it, right? And we might then, different fields might give different signs to different things, different elemental units within physics or chemistry might have different signs that they want, different mathematical properties we can assign different ways. All right, so one more slide on semiotics. So of course the written word is really a complex semiotic system, but we're always adding new symbols, especially if you get into mathematics or fields like that where they want to add new symbols because they come up with a new concept. They want to be able to express that quickly, succinctly, each time and repetitively. Right, so for signs, again, we want to be able to kind of figure out what's going on the first time we see it. So this isn't great resolution, but maybe you can see there's a couple of gears here, and these look like fingers, right? So you don't have to have it explicitly explained that maybe it's a bad idea to reach into whatever's going on there. And then also, one of the kind of natures of signs and symbols is that they have different cultures, right? Assign the same meaning to different symbols. And so here I've used the monetary symbol for a handful of cultures. So in the United States, if we see a cartoon and they have dollars in their eyes, we know what that means. But if they put this yen symbol in their eyes, we might not get that right away. All right. I want to talk briefly about kind of this notion of denotation and connotation. I'm going to start with these concept of P reps, which is basically short for physical representations, and C reps, which are conceptualized representations. So I have an example on the next slide, but basically this is, P reps are things that it's pretty obvious if you have something pictured, you're trying to represent something that looks like that which is pictured, whereas C reps, we're trying to do things that can't be you can't just see, right? Like emotions, right? So if you want to represent emotions, you have to put like a sad face or something like that. And so the picture isn't really showing somebody crying or whatever, it's trying to show sadness or risk or something like that, right? So you can't see risk, but you can have a picture that you see as a risky situation and understand that means risk, right? So that's what these two concepts. Denotations and connotations are very kind of along the same lines, right? In that denotations means the literal meaning of what you see. So if I have a chair in a picture, it means, a place, it's a chair you can sit on, right? Now, if I put some manacles on that chair and some wires to it, right? Now I'm implying something else. I'm implying that we're talking about, the death or the death penalty or something like that. And so it's not just a picture of a chair, it's actually trying to say something more than this is a chair, right? And so we can have similar items in the same picture, but use them for different things. All right, and so to just go to something a little less nasty, I'll talk about mathematics in those two things, right? So we can have this mathematical expression, which means this line, right? Y equals 3x plus 2. And so this is not really physical representation. Well, it's a physical representation of a line, I guess, but it's really more of a denotation. But we can take this same notion, a mathematical equation, like E equals mc squared, and that has, for most of the times you see that, it doesn't mean energy equals mass times the speed of light squared, right? It means science, right? Or smart person. And so that's really what people are trying to say when they put this on a poster or something like that. They're not usually talking about the general relativity. Right, so that's kind of a brief talk about those two notions. I'm going to spend a little bit more time on this notion of perception, specifically Gestalt, the Gestalt approach to perception. Now, Gestalt began as a psychological school of thought in Germany about 100 years or so ago, but it's kind of lost its luster in the psychology departments. It was kind of a, you know, this seems to work, right? This seems to work. And so it wasn't really a good way to study how the human brain perceives things. But it does actually work pretty well if you're trying to design things. Well, this works for just understanding, this works for understanding, right? And so it's held on as a design concept more than a psychological tool. Right, and so basically the word Gestalt in German means analysis of perception of form. So we're no longer doing the analysis of perception, we're more focused on what forms work well in design, right? So this is an expression you've probably heard before, the whole. Well, you've heard actually a variant of this. The whole, you've probably heard the whole is more than the sum of the parts. That's actually not the original quote. The original quote is the whole is other than or different from the sum of the parts, not necessarily more than. But that's been lost through the years, right? Anyway, this is kind of one of the key concepts of Gestalt, is that seeing the whole thing together is different than all the components. And so someone's put together this little Gestalt symbol, which shows a lot of the elements of Gestalt, but I'll talk more about each of those, right? In the slides coming up. So there's this Gestalt approach to perception has kind of 4 overarching properties, and then among those, there's 13 principles that apply. So here's the 4 overarching properties. I'm missing one of my pictures. I guess it's on the next slide. All right. Right, so I'll look at the pictures on the next slide. So emergence is this notion that you see the whole concept before you see the little individual segments of it. That's emergence. Reification means that if there's something missing, we're experienced enough to know what's missing and then kind of fill it in for ourselves. Multi-stability is where there's things that could go one way or the other. So this, I'll show on the next slide, this vase versus faces is an example of that. And then invariance is that we're pretty good at recognizing when things are different and when things are similar. So to dive into each one of those with a specific picture. So this is emergence. If you haven't seen this picture before, there's a dog in this picture. It's a Dalmatian, so it makes it easy for the black and white spots to be masked, right? So, and once you know that there's a dog in this picture, you can spot it, but it might take a little bit. But at some point, if I hadn't spoiled it for you, you would have found the dog in that picture. And there's a tree here, right, with some mulch around it. Reification is this notion that, all right, there's these 3 Pac-Man symbols here, but really what I see is 3 circles with a white triangle on top blocking it. And this thing here is like a snake wrapping around some cylinder. You've probably seen this kind of worm or dragon thing where you just see the parts and you assume that there's a ground plane or a water plane that it's breaking. And then all these cones obviously represent a 3D sphere, even though really it's just a bunch of, well, they're not all triangles because the bases have a little curvature to them, which helps give the 3D notion, right? So this is reification, seeing what's missing, right? And these 2 up here represent the notion of multi-stability. So we saw the vase on the last slide. Is this pair of faces staring at each other or a vase? This one here is called the Necker cube. And at first glance, it might not look like it's a multi-stable object, but you can think of it as either a cube that's going out this way or a cube that's going down this way. And sometimes generally one will be more obvious to you from the start, but then if you stare at it long enough, the other one pops and then you can't go back. So sometimes that happens. And then invariance is, we need 4 pictures to show that, because if you look at this picture, the A section here, all these objects are the same, right? And you can recognize it pretty quickly. They're just rotated differently, right? Whereas in the B one, you can pretty much see pretty quickly, even though they're rotated, to kind of disguise the fact that they're not all the same, but we see pretty quickly, you see that these are not the same, right? In C, you can see that they all have the same kind of topology, but that they're warped a little bit, right? And that jumps out pretty quickly. And then in D, they have different rendering styles, but again, they're really all that same object. And so we're really pretty good at knowing when an object has the same form, the same shape as a three-dimensional shape as another object, even though it's two-dimensionally rendered and twisted around and tried to disguise when that's not happening. So those are the four properties, rather, of Gestalt. And those lead to 13, let's check how I'm doing for time here, 13 different principles of design that come out of those. And again, here's kind of an overlay. Some of these are redundant with what we already saw because there's some, they take from those four properties. I'll try to maybe skim over them quickly. So these are the general things. So, right, the law of prognance. So this is like these semicircles, right? But we just see 5 rings interlocking, and we see that right away. And so we don't break it down into its component parts. That's really what this is saying. Closure is this notion where we see things, right? We don't see in this case, 4 Pac-Man symbols. We see a couple of sheets of color on top of 4 circles. With this World Wildlife Federation logo, there's these dashed lines represent what we fill in. Those don't actually show up there. So this is representing closure. Symmetry and order, right? We see pairs of eyes. We see pairs of parentheses, curly brackets. And figure versus ground. So again, the faces versus vase, right? Sometimes we see the vase as the ground, and sometimes we see the faces as the ground, and therefore the vase is sitting on top of that. And then here's kind of a really simple example, right? A white square is the foreground, and the black, in this case, is the background, and vice versa for this one. For the other ones, so connectedness, right? So normally we might see these yellow things as being connected because they're both the same shape and same color, but we understand that they're touching this green thing here, which represents a stem, and we know a little bit about flowers to know that those go together. Grouping, right, is pretty obvious. So if you group things, they seem to belong together as a set, and that can happen by being near or just being outlined, right? So these belong, these don't belong. Here, there's sets, and this set has kind of 2 subsets, right? So that's proximity. And then pretty obvious, right? We assume lines kind of flow smoothly, and it doesn't go like a dichotomy or a discontinuity rather here and another discontinuity. We presume there's some continuity on things like that. And we're going pretty fast, so I'll just keep going. So common fate is hard to show in a still picture, but basically what happens here is we have these 4 dots. 2 of them go this way and 2 of them move this way. And so we then presume these 2 belong together, which have moved to the left, and these 2 which have moved to the right belong as a unit. And so if we see this in motion, that's what we're going to see. If things are parallel, we kind of see them as belonging together. And then again, if things are similar, right? So these are all squares, so they belong together, but also there's different colors that kind of belong together. And in this case, different shapes that belong together. And we can pull those things out, which I'll show in a moment. And then the final 2 are focal points. So we have things that draw our attention, right? So we have a constant pattern that serves as a background, and then something kind of bold in the middle that draws our attention. And then this one, right? So past life experiences. If we see green, yellow, and red in a row, we kind of get a gist of what's being said, right? And if one of those is brighter than the other, then we know whether to go, stop, or be cautious. At least here. So, well, that's much dimmer than I thought, but here's this notion of thinking about things. We were talking about human cognition versus perceiving things rapidly. They're all kind of a little more washed out than I thought, but pretty much your eyes are gonna spot that one of these, of all these objects, all these little circles, one of them is a different color, and we don't think about that, right? That just happens. And so same here. So this kind of happens. Does anybody want to read me what this says? ABC, are you sure? Did you see what happened here? This is the same thing, right? So, yeah, well, I changed the slide. No, but I'm saying, are you sure this is are you sure that's a B? Right? Because it doesn't look like it changed, right? So Context does a lot for us, right, immediately. A lot of times when I spell my name, I put it like this, and my kids are like, why'd you write a 13? I don't understand that. An illusion you're probably all familiar with, right? Which of these lines is longer than the other? They're all the same, of course. I'm sure most of you have seen this illusion. But this notion of these arrows on the ends tells us, kind of causes one to perceptually stretch or shrink. One of the theories for that is that we're seeing things as if they were 3D, and those arrows are really telling us it's the corner of a box or something like that. I don't know if this is settled science necessarily. Another illusion I'm going to guess most of you have seen something similar to, right, is which one of these circles is darker than the other? Which color is this? Right, so for me, this looks kind of brown. This looks kind of orange. But in fact, of course, they're the same color. It's really just the context that this shows up in. If you can even see, my eyes, especially from off to the side here, it actually looks like there's a gradient from orange to brown. But if you look at it more closely, you see it's actually the same color the whole way across. So context does a lot to mess with our perception. All right. So also there's some more multi-stability, right? So what is this a picture of? Some people will see the lady's face really quickly. Others will see the sax player of a rather large saxophone. This one took me a while to see. So I see the flip-flops really quickly, but there's also the shape of the Coke bottle right in the middle of the can there. So those are both multi-stable shapes. Sometimes there's things, this is like the Dalmatian one, right? There's a picture in here that may jump right out at you at first, or may take you a while. But once you know that this is a picture of a cow, right, you probably see it right away. This next one stymied me for a long time. So does anyone see, what do you see here? So you see it right away. See, I saw this as a rock in the wall. Maybe the picture's too big. But when I was, someone showed me this and showed this as a representative of an illusion. And I, for the life of me, did not see the cigar. I said, what's so special about this picture? So he had to tell me there's a cigar in there. I was like, oh, there it is, right? Yeah. And once you know it's there, right? There's no stopping it. But it just looks like somebody stuck a rock in the wall and took a picture of it. But not quite. So everybody see the cigar? Yeah, once you do, and maybe this is a little too big, or if you've seen it before. So anyway, kind of represents a danger of visualization, right? You might think something is obvious, or maybe you're deceptively doing something, right? In the case of this photographer, I'm sure they were deceptively creating this picture to fool us all. Right? So that kind of shows us a little bit about this notion that our pre-attentive vision isn't always spot on, right? We showed a couple examples, right, earlier. So you can spot the circle in this pattern pretty quickly, right? And we saw that with the colors earlier. But in this case, our pre-attentive vision doesn't work so well because we've kind of disguised the fact that there's one red square in here, right? There's one red square and it's hard to find maybe. I mean, I know where it is, so it's right there. But because there's too much information, there's too much disparate information, it makes it harder to find. So these are the kind of things that we want to watch out for when we're doing visualizations. And then one or two more slides here on comprehension. So these two plots, right? So this plot here is the age of Miss America. I don't know why there's a gap here. This plot is the age of Miss America. And this plot, the yellow one, is the murders that are done by steam or hot vapors or other hot objects. And they follow, except for this little blurb, right, they kind of follow the same pattern. So this is this concept of apophenia, which basically means if we see a pattern, we're going to say, oh, there's a relationship, right? But so you might think, well, obviously, we want to have younger Miss Americas, so there's less murders caused by steam, right? But there's no real correlation, right? So there's a book, I forget the author's name. So here it is, Tyler Vegan. He actually has a book where he's gone and just found lots of data sets and cross-analyzed them all until he finds these crazy relationships. And so he has a whole web page and now a book that show a lot of these relationships that, you know, have no causality. Okay. I want to talk a little bit about taking your data now and mapping it into something that works for human comprehension, right? So the word mapping comes from this Latin mappa mundi, which it means basically mappa is like cloth or napkin. So it's a napkin of the world where you might draw your map on cloth. And so that's where we get this notion of what map means. Of course, we understand it originally as cartography, but we use it in mathematics to talk about this is maps to this. It's a relationship. And we use it in visualization and data science to say we're going to take this domain and map it to this other domain or region. What's that? I forget the other word. Right? So we're going to do things like map colors to concepts, right? So red might mean faster, or a sound, beep, 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 you know, or more beep, 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 right? That tells us that somebody's moving backwards who can't, you know, who doesn't have good vision, right? Or in another context, red might mean oxygen atom, right? So there's these different cultures use different mappings, and so something we have to watch out for. And when I say culture in this case, I mean scientific community, right? And so in some cases, and maybe Enrico, you can correct me if I'm wrong, is red mean increased temperature in astrophysics, generally? Oh, it's the other way around? I'll have to fix my slide then. This is a notion that we've been using for a while, and I can never remember which way was which. And then I think in geology, it means decreased density, right? So if one means higher, one means lower. I happen to get it backwards here, but one of this notion of mapping, right? And so in this peg, going back slide, going back to our notion of atmospheric sciences and thunderstorms, here the orange particles are flowing upwards and the blue particles are flowing downwards. There's also these streams. The yellow ones are going faster than the orange ones, right? So there's ways to map colors to different things. And then water vapor is mapped to gray to kind of match the notion of a cloud. All right, so a couple more slides on this notion of, or I'm going to start kind of talking about data rather. So when we look at data, especially when we're presenting it, we can break it down into quantitative data versus qualitative data, and both have their role in visualization. So if we have quantitative data, it means we want to see the numbers, right? We want to get down to the details, and that's often important. But a lot of times we're going to start with the qualitative, just kind of get the general trend of what's going on. And again, as it says, if you have a lot of data, you can get some overviews and see what's going on. And then use it kind of to simplify data, right? So we might just even use it to say something is hot or cold, right? So we break it down into large discrete chunks rather than as a continuous data set. So sticking with our weather theme, here's a couple of different ways of representing weather over the United States. So the first one is a lot more quantitative. It has temperature, it has wind speed by these sticks that come out, and wind direction from the sticks that come out. The circles, if they're filled in, the more they're filled in, is showing us cloud cover. Then it has some discrete events like the little yellow bar with a zigzag by it are thunderstorms, and the little infinity signs are fog, I think. And then the yellow commas are rain or precipitation. So this is the kind of information a pilot wants if they're flying across country. But if you're just the person riding in the plane and you're going to be flying to Denver, you don't care about all the details here, right? You just want to know what's the temperature generally, is it raining or sunny? You know, do I need to bring a sweater? Do I need to bring an umbrella? That's the details you want. So you're more interested in this kind of overall feel. Looks pretty sunny out west, kind of rainy in the northeast and around Chicago, right? We don't, if we're not flying the plane, that's all we care about. We can break that down, at least in the quantitative measurement side, we can break that down into these 4 categories, which I think statisticians like to use to say, what can we do with data if if it falls into this kind of type, different level, I guess we'll say. So nominal basically means all we know is that the name of an object, or we can classify that object into some group. Ordinal means we have a ranking between objects, but not necessarily a measurable ranking. We just know that they're in some sort of order. Once we get down to interval, we know specific measurements between different units. And then ratio has that, plus it has an absolute zero. So if you're using, say, Fahrenheit, right, you can't say, oh, it's 20 degrees today and it was 10 degrees yesterday. Today it's twice as hot as yesterday. That's not true, right? Because the zero in Fahrenheit is not absolute zero. In Kelvin, there is an absolute zero. So if it's 300 degrees, and then one measurement is 300 degrees, the next measurement is 600 degrees, the 600 degrees is twice as hot as the 300 degrees in Kelvin, right? So kind of give what operations you can do on those four things. It's in words over here and words and chart over here, right? So if you just know what an object is, you can count them for frequency. You can figure out, what's the most of, right? You can figure out the mode. If then you know the ordering, now you can sort them, or you can calculate some sort of median, right? Which one has the most, if you do like a little histogram. Once you have intervals, now you can do simple mathematical operations, addition and subtraction, and calculate differences. You can calculate means and standard deviations, right? So you can't calculate the standard deviation on something where you just know the order, like strongly agree, agree, don't care, strongly disagree and strongly disagree. You can't calculate the standard deviation on that. And then if you have the interval, you can do that. And then with the ratio, again, you can do multiplication division, which means this is twice or half of this, right? And it means that you have to have this absolute zero. All right, so we're going to segue into talking a little bit more about data and revisit our Anscombe's quartet here. Right, so that's just kind of XY plot data. But there's a lot more types of data then. So we just went through ordinal data, right, was one of the things we had. So data with orders. Categorical data, which was that nominal. So this is somebody else's chart. So this is nominal, ordinal. Then they just have quantitative. They don't actually separate quantitative into interval and ratio. But we know that there is a difference there. It's what operations you can perform on those. And so they've grouped all of these things that we've just talked about as quantitative numbers, or as tabular data. You can also have relational data, right? Who's talking to who knows who, what computers are connected to what other computers, what actors are in movies with other actors, right? So that's relational data. And then you can also have spatial data, right? So here we have just essentially two-dimensional data mapped onto a three-dimensional sphere, right? And this tells us something. So this means that data belongs somewhere, right? You can't just move it around. This data for near Paris here belongs near Paris. Whereas these other data things, we can kind of move them around and place them different places in our visualizations, right? We'll probably, I think we're gonna cover all three of these higher level things over the course of our workshop this semester. When we talk about pair view, we're going to talk mostly about kind of quantitative data and spatial data, but when we get into other things, we'll look at relational data and things like that. So if we have this, again, going back to the left side, we have this tabular form. It basically means that we have all these data points, and then there's a bunch of items about that data, some of which can be spatially based, right? Some of which is categorical. And so they all have these different properties. And then we can do this other breakdown here, right? So we have data sets that can be kind of tabularized. This is also breaking it down, right? Tables, which is that left one. Networks, which is our relational data. So this is from, oh, I don't have the picture. I think from a couple of slides ago. So some of this breakdown comes from this book by Tamara Munzner, Visualization, Analysis, and Design. I think it came out in like 2013, so it's a pretty recent book. So that's where some of these pictures are coming from. Once we've decided what we have, though, there's other things that we can know, right? So we've already talked about categorical, ordered, and quantitative, which there's two categories of that, right? if we have an ordered data, it can be two different ways, right? Ordering can go one way or both way, or it can be cyclic, like if it's time-based, right? So we have some sort of daily diurnal pattern that we want to see that's time-based, and we'll see that in an example later. We can have, a two-dimensional table, three-dimensional table for XYZ position, or spatially based on terrain. We can also, another important dichotomy is whether the data is a one-time piece of data or it's moving, right? It has some dynamics to it. So we're going to look at different examples over the course of the semester for all these different things and different ways, different attributes, different ways to process the data. All right, so from her book, Tamara kind of divides visualization into scientific visualization, which is mostly the focus of what we're talking about this semester, but we'll delve into information visualization a little bit. But basically for most, and this is not necessarily, especially if we're talking maybe social sciences and demographics, well, demographics maybe has spatial position, but that there's an assumed spatial position. If there's an assumed spatial position, then a lot of times we're going to consider that more of the science-based. Whereas if you can move objects around and create your own spatial relationships which helps you maybe reveal patterns, then at least in Tamara's dichotomy here, she calls that information visualization. All right, good. How we doing? All right. Right, and so if we're doing spatial visualization, or in her classification, scientific visualization, right, that means that there's a bunch of data, so there's a cell, which is like, one of those items in our table, or Excel spreadsheet, that has at least some sort of spatial information about it, X, Y, or latitude, longitude, X, Y, Z. And then, for example, if we're doing some sort of CAT scan, CT scanner, with a medical imaging instrument, then we're going to have a 3D volume that comes out of that. And so all the data points we get, all the density values we get, have an X, Y, and Z value that's associated with it. And that's kind of the day we're going to look at next week, but it won't hold for the whole semester. We're going to try and be more broad than that. But for next week, this is kind of the bulk of the data we'll look at. And I want to talk a little bit about the notion of data. So this is from a website from Bloomberg. And so this is a little interactive page that they created to talk about amount of data. So this, the y-axis here is how many pieces of information are there for a particular data set. So from 1-ish to over 1 billion, right? So these ones over 1 billion are basically the human genome data, right? So you have lots of data for, in this column here, so I should say the x-axis is number of things we're talking about, right? So this is one person. We have over 1 billion pieces of data for that one person because we're studying their genome. Whereas if we move here, different sciences tend to have more information about different, and it's not always people. In this case it is, because this is US Census. But now we have data for a lot more people, but a lot less data per item, right, in this case. So this is US Census data starting back in like 1860 or something like that. So there's a lot of data, but it's about a lot of people, whereas here, there's a lot of data about one person. And this spot here is they're trying to collect 2,300 people's genome. I think it says they're up to 1,700 or so at this point, so, or when this graph was made. And most of these data sets actually that are on this plot that Bloomberg created are available open, right? So you can actually download a lot of these data sets. If you put your mouse over a point, it'll tell you what the data set is. And if you click on it, you can go to the URL. Now, some of them, of course, are broken links. But if you want to like get different types of data to experiment with, you can actually go to each of these little dots, and it'll tell you more information about it. They've kind of broken out 3 of the categories for you, but then all the other little small dots are just data from different sciences. So there's some data you can look at. So now I want to talk about, we've already looked at some concepts. I want to look at some good visualization concepts, and then we'll look at some bad visualizations after that. And then we'll wrap up with a video or two. So here's some, actually before I get that, I'm going to jump back to that slide we just looked at. So one of the things I don't like about that slide is that both of the axes are basically the same thing. It's amount of data, right? They're both logs, so that's fine. The thing is, they stretch the x-axis, you know, by a factor of 2 or so. And so, you know, in theory, if you had a dot on one side of this red line and a dot on the other side reflected over that line, that's the same amount of data. But it's hard to see that without drawing the red line because they've stretched the x-axis relative to the y-axis. And in my mind, that's bad visualization design. It should have looked more like this, which I've squished it here, so that you can see if there's a data point here and a data point on the other side of that red line, that's basically the same amount of data, or here and here, right? It's the same amount of data. This is just on the, if I move to the right on the x-axis, it's more items I'm talking about and less data, whereas here it's less items but more data per item. But it's the same amount of data if I see that reflection over the line. All right, so there's a hint of what's to come about bad visualizations, right? But before we go to the bad visualizations, here's some rules of thumb for better visualizations, improved visualizations, which will include also some counter examples, right? I mentioned Edward Tufte earlier. He's trained as a statistician, but he's really become known as one of kind of our foremost visualization experts, especially when it comes to static design that reveals patterns quickly. So he was hired even to do things like create the representation of the bus schedule for New York City buses, so that makes it easier for bus riders to know when to expect the next bus, right? So I have a slide for each of these, so I'm just gonna skip over that. So one of his things then is to maximize the data to ink ratio. So in other words, less ink for the same amount of data is a higher ratio. That's good, right? Or more data without increasing the ink is better. So you might start, one of his kind of classic examples is, here's a plot, right, for 9 months of some percentage of something. We don't know what it is. But it's got all these lines all over it, which in some sense tells us we can do better comparisons. But if we're just trying to get the overview of what's going on, these lines kind of get in the way, right? I mean, we can go back and look at the numbers later when we need to, but trying to get that overall view, which is part of what we do visualization for, it's in the way. So he starts by removing the lines, then he removes this shaded color in the background, so there's more contrast between the data and the empty space, the foreground, background stuff like we talked about in the Gestalt. And here, actually, so this, I guess this one is just a copy over for this one. So this next one, the middle one on the bottom, it's actually removing ink, but it shows us where these 5% increments happen on each of the bars. So now we're actually getting more data by lightening taking away ink from certain places. And I'm not seeing the difference between that middle one and the right one. What's that? Oh, the y-axis. Oh yes, tick marks on the y-axis, and also I guess the line on the x-axis they removed. All right. So according to Tufte, and I think generally it's good. I mean, it's probably, there are going to be counterexamples too, right? But the less coloring you do per data, the better, right? That's that theory. So she calls, this is, again, this list from Tamara, this notion of lie factor. So, and it took me, I had to figure out what's the lie here, right? So this actually segues into our next one. Does anyone see what the problem with this graph is here? Took me a while to figure. Actually, I had to ask somebody. So go ahead. Right. So it's a pie chart that they've turned into a thick pie, like a big wheel of cheese, and then rotated it this way, right? So there's more green down here that really isn't part of the pie chart. So the apple percentage looks a little bit more than the apple percentage should look, right? And then that, because we're looking away from it, it's tilted away from us, we don't get that same effect on the other ones. We only get it, a little bit of the orange here, but mostly the apple shows up as bigger than it should be, right? And so there's a little diagram here. So, right, so here it is, that cheese wheel turned way down. And so here's the apple segment where it's, you know, even bigger lie, because we'll get a lot more of the green here. But it's a little more obvious this way, right? If you just tilt it a little bit, then you're lying just a little bit, right? So that kind of segues into this next notion, which is don't use 3D when you're not showing 3D data, right? And there's no point of it. What it does is it occludes, right? You block other data. Here they kind of had this camera angle where, you know, there's purple here, but we only see half of the purple because there's another column in front of it. Actually, I think I can use my mouse to draw on here. Well, there you go. For those people who are watching remotely, right? So some of these columns, you know, they've taken care to see through this column or next to this column, but it still shows us more of the front column, which gives us a sense of bigger than for the other ones, right? And the same goes for the chart on the right. So we have occlusion. We don't even know in this chart on the right if there's any green in the far back left corner, right? We can't see that at all. It might just be too short for us to see. So don't do 3D if you don't need 3D. This next one is one that argues against, even if you have time-varying data, argues against animating it. And that's so that if you want to see patterns, diagonal patterns, and we'll see another positive example of this in a little bit, it's easier to see it all at once and to see the things that are happening. If you're watching it over time, you can see that changes are happening, right? So if I look at these two pictures, if I look at, let me use my mouse for the other people. If I look at, say, these two pictures right here, I'm not going to see a big difference there. So again, this is if I'm looking at the overall pattern, it's better to see it all at once. But if I want to see what's happening, right, I might see that, you know, step 5 here, where'd my mouse go? Step 5 or 6, I can't really see that that's different from the next step. But if I'm animating it, I can actually see if there's small fluctuations happening. So I'm going to argue against this one to a half a degree. All right, so depends on what you're trying to show. So in some cases, you want to get the overall view. It's good to see it all at once. If you want to see whether there's some minute fluctuations happening, then it's better to animate. And the same can be applied actually if you take your data and add and put it to sound, right? If you what we call sonify that data. If you're listening to sound, you can hear very subtle pitch changes that you might not notice visually. So you can, if you're like, say, varying a color, it might be too subtle to notice. Whereas our ears, unless you're tone deaf, our ears are pretty good at recognizing slight pitch changes. All right, so the next one in her list is focus and context. So we saw that with the big hello, right? So you want to start, excuse me, right, you want to zoom in basically, right? You want to focus in. So we want to start with the global view that give us the context and then zoom in to get focus, right? All while not hiding anything. And I think the next picture shows that a little bit and also talks about doing this in an order, right? So the 6 and 5 are related. So we might start with the overview, and then you've seen this before, where you do a little breakout box and then you zoom in, right? So this is context and then focus on a certain area of what's going on. And then in this case, actually allow you to get to the numbers, right? So in this case, they're talking about an interactive thing where maybe we can move these boxes around. And so once we get the context, if we find something interesting, we can zoom in on that. I'm going to move my microphone and cough for a minute. All right, and then finally, this kind of goes back to number 1, right? Under-engineer if you can. Don't add more than you need to because that just kind of deflects from the data. And so if you want to have, if you're doing interaction, make the interaction simple. If you're showing data, show as little as possible, right? So here, they're just showing the data, and yet we recognize this as a equirectangle representation of the Earth, of where the continents are. And so we know basically what the context is without having to actually draw the lines around the countries. Uh-oh. Okay. And that we can actually see in this next picture. So this next picture, the only thing being drawn in this picture is roads, nothing else, right? And yet we know what it is. We know where cities are, right? Some of the roads are thicker, and so we can see where interstates are. We know where mountains are because the roads are affected by the mountain ranges. You know, we know where the water is. We know lots of information here, and all we've drawn is roads, right? So here you can see sparse roads, but you can actually see the road patterns in there. So it's a lot of farmland, right, or rangeland. Right, so by putting all this dense data on here and nothing else, we actually see the overview of what's happening. And then you can, again, zoom in on that. So I've alluded to this picture a couple times. So this data is from Jan Ayert, who's some of these slides I borrowed from. And so what he did was he took when he's sending emails, right? And he started back in 2005 and went till 10 years later. And so these are the times when he hit enter and he's saved up all his emails and he analyzed this. When did he hit emails, right? And you can see these gaps then, right? So here's when he's taking lunch. He's not sending as much email. So this is going up in the day, right? The bottom is the beginning of the day. Let me use my mouse here, right? So, so the arrow's pointed out too, right? So here's lunch, here's dinner. So it says he's got it annotated. So if you see, he moved from the UK to Belgium and there's a 1 hour difference. So his lunch became an hour earlier, but then at some point something happened here. He says bug, and I don't know whether he means bug in his analysis or he was trying to debug something, and so he was sending a lot of emails to somebody. But at the same time, he stopped taking lunch, right? So he stopped having lunch in Belgium. He doesn't know what happened here, right? So maybe he lost some of his data or he took an extended vacation. I don't know. Anyway, so we can see again, so here's a cyclic time, right? So you can see nighttime at the bottom. It's cyclic time, so he just repeats it. Each column is a day, and so he just repeats it over and over in a cycle. And then time for the years is on the x-axis. And so it shows a lot of stuff. And again, all he does is put a dot at the time when the mail was sent. He doesn't have any other thing other than these annotations that he's added. Oh, we're almost out of time. So here's a few bad examples of graphics, right? So this chart, I mean, this one's unbelievably bad, right? So why are they using a pyramid here? Because it's pretty, right? The thing is, what's the second most biggest chunk of this? The little purple thing on top is the second biggest number of percentage here. But because it's on the top of a pyramid, it looks so much less. Here's one that's just totally ridiculous, right? So here's this picture's miles per hour from one year to the other, but where's the zero on this? The zero is like, 20 feet below us. It's like, well, is he pitching half as fast as he was last year? No, he's pitching 2 miles an hour less than he was the year before. So just crazy. This one's a little more subtle. If you look, all the lines are half a percentage difference, except the first one. They skip 0.05. They just go straight to 1%, but it's the same measurement. So it kind of offsets whether we're looking at something. And this one, I think is pretty obvious. You can't read anything there. This one's kind of crazy. So this one's showing drinking ages in Canada. There's only two, based on provinces, there's only two values, 18 and 19, yet for some reason on the y-axis, they have these incremental things that don't even stop at 18 or 19. And here's another bad one. So this one is just data that's really an XY plot, but they've masked it with the United States on top, so you can't even see the data where the Great Lakes and Canada are. And so you might get the impression that Maine has something going on in it, right? Because it's 8%, but it really has nothing to do with Maine. It's just, it's a time value. Maine just happens to be in the rightmost part of the United States. Here's another bad one. So this one has, if you add up the percentages, like 300%, because it's not really, it's not telling us, it's not a piece of data that's meant to be divided up like that. All right, so those are our bad visualizations for the day. I want to talk briefly about batch versus interactive, and then we're at our time anyway. So this is really kind of jump into what we're going to talk about next week. So we'll talk a little bit about batch animation, or batch visualization, which means we program some algorithm, we send it off to a computer, it sends us back a picture or whatever, or a movie or something, versus interactive, where we use our mouse and find out what's going on. So with interactive, we can explore more, we can get immediate feedback, but a lot of times if we have a huge data set, it means we can't see the whole data set, or our computer's gonna be really slow and it's painfully interacting, right? Pain interaction. Whereas if we do batch, we have to predetermine everything, but it lets us do big data and it lets us work on our big machines. The picture, here's a preview of the virtual reality visualization, which we'll do in a few weeks. So what I like to think, instead of batch versus interactive, is that they work kind of together, right? We start with interactive, And then we do some exploration with a reduced data set, find out where the interesting areas are, where if we have a data set that's too big to fit on our desktop or our laptop, now we send it to the big machines and do some batch animation, but it's guided by the interactions we did. All right, so I have some videos which I'll show after I dismiss if you want to see them. But I want to do one brief thing before we go, since time has run out. So next week we're going to talk about peer review. We have that and other tools available on the IU High Performance Computing Systems. So if you, next week when we talk about peer review, if you're, I don't know about the Crane people, if it's going to work for you, but if you're at IU, you have the ability to get an account on any of our high performance computing systems. And so we're going to work on a system called Carbonate, which provides us with this interactive GUI desktop called Research Desktop, or RED. And so you can go to this URL, access.iu.edu/accounts with a capital A, and get an account on Carbonate. And then once you do that, you can search for ThinLink, which is on our knowledge base. And that provides you, it's basically you see the desktop of the supercomputer on your desktop. It's like shared things, V and C if you're familiar with it. It's available for all three major computing platforms. And by doing that, you get software that we install for you, and you have access to the supercomputer with a lot more RAM. Now, for those of you who don't want to do that or can't, what we're going to talk about next week, peer review, you can actually, most of the examples we do next week will not require a big machine. So if you wanted, you could download peer review. I don't have the URL. I forgot to put the URL here, but it's peerreview.org. And then there's a download button, and they have pre-compiled for, again, the three major platforms, or if you want to compile it, you can do that. I'm going to do step-by-step stuff next week, and I'll probably be doing it live, I think, depending on how well I have practiced. But anyway, and you're welcome to follow along, but we're not going to say, wait for every single person to get every single step along the way, because we only have an hour and 15 minutes. And so I want to try and squeeze as much in as I can, but we can help you afterwards if you get stuck somewhere, or follow on later. So that's for next week. And so that's it. Any questions? I'll show a couple videos if people want to stick around, just short videos.
Quick unrelated to Carbonate, is that what Karst?
So Carbonate is the next generation of Karst. So Karst itself will exist, but it has a desktop, but the desktop portion of Karst is going away in December. I don't know. Yeah, I don't know. Any other questions? Dave has a comment or question? Oh yeah, go ahead. Here, wait. Well, I guess this is applying to local. All right, Dave has a comment for the local people here. All right, we do have a few undergrads here, so that's good. All right, let me show maybe a couple of videos here for those of you who want to stick around. I have them queued up.
My only concern with spatial data is the modifiable area unit problem. And are you, I'm assuming familiar
Right.
with the modifiable area unit problem? That data collected at one scale is appropriate for use at that scale, and that's something that I see happen quite a bit. Is now with the ubiquity of data, I can get it, I can plot it, and IPy leaflet, do whatever that we don't.
Right. That should be something probably that I sneak into that talk there.
Mess up. It's like, oh, I've got this data, it's a boundary, I can use it to define, this area. Well, no, it was collected at a 100,000 scale. It's
right.
Trying to use it as data set.
At some constant offset angle, rotating hundreds of times per second. We can detect pulsars as these emissions, traveling across many light years, are intercepted by a radio telescope. Because a pulsar's frequency is rock steady, pulse arrival times can be predicted with extremely high accuracy. If the pulsar was to move away from us for some reason, this would be reflected in pulses arriving with an extra delay. If the pulsar was in a binary system with an object such as a planet, this delay would vary periodically. However, this situation is indistinguishable from that where some periodic motion is occurring on the receiving end but has not been accounted for. Such was the case with the British discovery announced in 1991 and retracted in early 1992 after the omission was corrected. Concurrent with the British retraction, Alex Volshin from Cornell's Arecibo Observatory and his colleague announced the discovery of a pulsar with a more complex variation in pulse arrival times. Independent periodicities were extracted based on an orbital dynamics model. Applying Kepler's law to the amplitude, period, phase, and assumed pulsar mass, the orbital radius and mass of an individual planet is derived. Here, the first planet is shown with corresponding pulsar reflex motion. Similarly, the second planet is derived. Summing the reflex components from each planet results in a more complex pulsar motion. The third and outermost planet completes the system. Projecting the pulsar's path onto the line of sight and moving through time, we reconstruct the reflex motion of the pulsar. This explains the delay signal received. The resulting system is shown here compared to our own inner solar system with planet size scaled up for visibility. But how can we be certain that the signal in this case indicates the presence of planets and not just an unaccounted for periodicity caused by other phenomena? The proposed method of confirming the existence of these planets involves the fact that the inner two planets pass close enough during their conjunctions to noticeably interact gravitationally. As a result of the gravitational force between them, the inner planet gains phase and orbital radius, while the outer planet diminishes in the same. The effect of these variations on pulse timing is cumulative and increases after each conjunction, occurring about every 200 days. The next one will occur in late August 1992. The shape and magnitude of time delay variations caused by planetary perturbations can be predicted exactly and compared with observations. If these predictions match the measured pulse arrival times, this will constitute a confirmation that this pulsar does, in fact, have orbiting planets.
I'll stop there.